All right. Well, good afternoon, everyone. Welcome to our second seminar of April for our computer literacy seminar series. Today, we're talking large language models with Sophia Serrano. She is a PhD candidate over at UW Seattle in the computer science program. So I'm going to let her talk all about this. This is a follow-up from last week, just on learning all about neural networks and things like that. So turning it over to you, Sophia.
Thanks, Caitlin. So we'll pick up this week. So last week we left off talking about sort of the basic concepts that make a neural network a neural network. But there are still a lot of questions that we sort of left open between, like, okay, we have neural networks that have been around for a little while, and we have large language models that have been around for not that long. So today we're going to try and sort of close that gap between talking about neural networks more generally, and today getting down to brass tacks and talking about neural networks that deal with text and the kinds of things that make ChatGPT both good at what it's good at and not so good at what it's not so good at. So with that in mind, just a reminder, last time we sort of left off talking about these sort of tools and tricks that we use to train neural networks. For example, neural networks that classify an image as containing, in this sort of toy problem that we introduced, right, one of three possible things in that image, right? So it's a bird, it's a plane, or a generic superhero. So that's not so bad if we're thinking about images, right? The nice thing about an image file is that it inherently has a grid of numerical values representing pixels, right? So if we're thinking about what the input to a neural network dealing with images would be, well, we can kind of take that grid of values representing pixels, and that already contains some meaning about the image. How about text, though? The problem for us when we're thinking about representing text as numbers is that it's not nearly as clear when you're first thinking about it how to meaningfully encode that text in numerical form. If we're going to have a neural network or any kind of neural model that deals with text, we need to feed it some numbers, but it's not clear what those should be. So the first part of what we're going to talk about today is some sort of strategies that have been developed over time for how we encode words in numbers in a meaningful way. That's going to be a first step that we're going to need for any neural network that deals with text. Okay, so to sort of motivate this, I want to walk through an example of what we do when we see an unfamiliar word. So it's possible that some of you in this room know what ong choi is. I'm going to let's for the sake of argument pretend that we don't know what it is if you do. And I'm going to ask, like, okay, what does ong choi mean? Well, if we don't know, well, we're not sure, but okay, suppose that we have these sentences that we can read, right? So perhaps ong choi is delicious sauteed with garlic. Ong choi is superb over rice. Ong choi leaves with salty sauces, right? So just like a collection of phrases from some data. And suppose that our data also contains the phrases or sentences, spinach sauteed with garlic over rice. Charred stems and leaves are delicious. Collard greens and other salty leafy greens. Well, we're kind of used to extrapolating to, like, okay, we might not know ong choi specifically, but we're actually pretty good at getting a sense of what ong choi might mean. And we're not wrong. Ong choi is actually a leafy green like spinach, chard, or collard greens. So that's all well and good, right? And it's an example of us using context clues, right? Like, we've been using context clues as we read and as we learn to read since we've been like little kids, right? It's like a classic reading technique that's taught for learning new words. It turns out that that's actually a really valuable basic idea for us to use as a starting point here as well. So our key idea is, if you have a good sense of the words that tend to appear around a particular word in your vocabulary, you actually have information about the meaning of that word. That's going to be the core idea that we're going to use as sort of a starting point for converting words into something that's numerically based. So, how are we going to do this? Okay, well, thinking again about the tools we talked about last time having to do with training neural networks, we can train a neural network to predict which word appears in the middle of some others. So that's a fairly general idea. Let's make this more specific. So the first thing we're going to do is last time we talked about having some sort of trainable parameters in our model, right? So we're going to allocate some trainable parameters, same as we did last time. In particular, we're going to allocate a particular list of trainable parameters, one of those lists for each word in our vocabulary. Predefine our vocabulary. Then what do we do? Okay, so let's say that in our training data, we have this text. I looked up when my dog ran to me across the room, for example. So let's suppose that we want to, when we're trying to predict which word happens like in the middle of other words, we can actually chop this up into a bunch of shorter segments of text, but just to pull one of those out as an example. Let's look at my dog ran to me. We can structure a neural network this way, and I'm going to walk through what this means for us. So what we can do is we can chop up this segment of 5 words into the 2 preceding words of the middle word and the 2 words that directly follow that middle word. What we're going to do with those is we're then going to look up the lists of parameters corresponding to the sort of outside window words, right? So this would be my, dog, to, and me, right? Each of these is just a list of trainable parameters. What we'll then do is we'll just sum those together. And one important thing that I should mention is how many of these parameters are in each of these lists. That is actually a free variable that we as a neural network designer can tweak with. Typically, these will be maybe like a few hundred dimensions in length or so. So not short, but a lot shorter than the length of our vocabulary, which often stretches into the thousands or tens of thousands. So what do we do with those? Okay, well, we're going to sum them together. So you know, if you're comfortable with like multivariate settings, this is a vector. If you want to think of it as a list of numbers, also fine. And then what we do is we project those, again, using learned parameters, into a vector or a list that is the length of the full vocabulary. Now, the idea here is that each word in our vocabulary has one corresponding number in this output list. And if the network is doing its job well, it should be assigning a higher number or a relatively high number to the slot corresponding to the word that actually appears in the middle. Now, one complication here is that you might note, well, there are a lot of different words that could have my dog and to me. So like my dog walked to me, I don't know, I feel like that's kind of a tired dog, but it could happen. So basically what the model is going to have to do is learn to give relatively high numbers to both ran and walked, for example, or walks or runs, right? But all of those are going to get folded into sort of the model's sense of which words tend to appear in the context of these other words. And if we think about what information the model uses to do that, the model actually has to compress all of the information it knows about these other words into these much shorter vectors. If the model is able to successfully compress that information into these short vectors, then it will be able to perform well on this final task. And so basically what that means is through learning to perform this task well and tweaking the only parameters that it has, this model is going to have to learn to encode some meaningful information about each word in the vocabulary into its corresponding list of parameters. First of all, does this make sense at a high level? Okay, great. Okay, how do we train this, right? That sounds great. It sounds great. Like, okay, yeah, if you have a network that knows how to do this, then great, we're done. We've already got some numbers that represent the words. You might be concerned about how we actually.
I was gonna come down and smash you with that other vacuum, the agitator. I was doing it, and I think the bearings are out.
Muted, Bill.
And it goes blah. I was like, holy shit. I mean, I thought the thing was gonna blow up.
For a second, I'm like, that's, I'm not
Yeah,
sure
I
where this question is going. Okay, okay, thank goodness. By that, I should also add, like, feel free to interrupt with questions at any point. It's easier for me to clarify stuff as we go.
And not vacuum cleaners.
Yeah. Well, I wasn't sure. I'm like, I'll wait for the question to finish and see how it ends. Okay, so how do we train this neural network? Well, okay, so let's think about some stuff we talked about last time. Where we ended up last time was in talking about loss functions that allow us to basically encode performing a particular task, right? So we have a loss function to quantify how well we're doing on a certain task. And by basically like trying to lower the output of that loss function through gradient descent, which is built on calculus, then we're able to perform well at this. So we saw this before, you know, with cross entropy loss for, again, a fairly limited classification task with only 3 outputs. But it turns out we can use the exact same loss for what seems to be like this much more complicated task. Fundamentally, this is still a classification task, right? Given a particular input, for example, my dog blank to me, right? We feed this through a neural network. So we, index its lists of parameters and so on, sum those together, project them out to the length of the vocabulary. And then what we're hoping for is for a high value for the word that in this case, in the data, actually turned out to be in the middle of those. This is basically just a classification problem. And so in terms of the machinery that we're using here, we're just using the same old cross entropy loss that we talked about last time, just with a size of the vocabulary length output vector instead of a vector of length 3. That's it. And we might also notice as we're looking at what we do to create this loss function, this is just the softmax that we talked about last time. Basically, we just exponentiate this vector and then normalize so that the model doesn't learn to trivially produce super high numbers for every single output word all the time, and has to actually learn to distinguish between when it should produce high numbers for certain words and when it shouldn't. And then we just penalize the negative of the number corresponding to the actual correct word. And it turns out if you do this enough times, your model will actually learn to get pretty good at this task. And so typically what this would mean is we have a lot of training data, right? Which in our case is just a big chunk of text, probably scraped from the web or something. And we chop it up into these small segments, and we end up with these vectors of parameters that encode the meaning of words pretty well. So backing up a little bit, one thing that I should mention here. So this is all well and good, but one problem that you might be considering at this point is like, okay, well, we've been talking about neural networks for text. Predicting a word that appears in the middle of other words is not the only task we might want to do with text, right? There are plenty of other things that we might want to build a neural network for that deals with text. And this doesn't seem to give us a way to do that. Well, you're not wrong. This is not the full way of getting a neural network to perform some arbitrary task of your choice that involves text, but it's actually a really key stepping stone. And the idea for that is that you actually can reuse some pre-trained neural network parameters. So this has been like a key idea in recent machine learning. If you look back far enough, it's called transfer learning in some cases. But the idea is, so we think back to last time, and we're thinking about gradient descent as basically navigating this landscape, right, where a lower altitude corresponds to doing better on our task, And the only things that we have to move are coordinates that have to do with like parameters of the model. Well, it turns out it's a perfectly valid thing to do to structure a landscape with a loss function, work your way to the bottom of that, and then change that landscape slightly, but still use those coordinates that you walked to as a starting point. This might seem like a weird thing to do, but basically what this means is that if we have this other neural network that we've trained, right, that has these sort of trained parameters that encode something about the meanings of these words, not necessarily the whole meaning, but something about them, we can essentially rip those out and use those as the start of a different neural network. And that often has proved to create a huge boost in performance for this eventual neural network. It gives it a much better starting place for figuring out how to put words together in a way that's relevant for the actual task that you want to perform. I'm gonna pause here. Does that make some sense?
So I guess
Yeah.
I have a question.
Yeah.
I thought that those vectors
Yes.
correspond to the goals, there will be some that is getting given, or are they not given? Are they being paid? Is it?
Yeah, great question. So I'm using this diagram as a sort of shorthand. In practice, so even though there are only 4 vectors listed here, which correspond to, I forget what my example was, my dog and to me, we would actually pull out the full set of these learned lists of right. So basically when I'm pulling out word embeddings here, you can think of it as if it's easier for you to think of it as like a list of lists or a matrix, either is equivalent, where one dimension is your index in the vocabulary, what's your word in the vocabulary, and the other is like which of the parameters for that word you're looking at. So basically you pull out the full set of trained parameters and they are not specific to any particular training instance. Does that answer your question? Great, okay. So yeah, this is a really general idea that motivates a lot of learning neural networks. So we've learned some word embeddings. What are we going to, again, we're thinking, okay, we're moving towards ChatGPT. We've got one of the necessary sort of ingredients, like a way to convert words into a meaningful set of numbers. What are we going to train those parameters further to do? And that's what this next bit answers. So ChatGPT and any other or GPT of choice, GPT-3, now GPT-4, these are language models. Now, language model is a fairly intuitive phrase, but for natural language processing researchers like me, it actually means something very specific. It refers to a very specific problem. In particular, a language model is a model that answers what is the probability of a particular piece of text. That might seem like a weird thing to ask ourselves, right? Like, well, if the text exists, then why do we care about the probability of it, right? Like it's text, you know? We care about it because that, like, determining the probability of a particular piece of text is what allows the language model to judge what looks like language it's seen and what's probably out of distribution for language it's seen. So in other words, if I say something like, I don't know, whiskey rubber duck, that's a low probability, like especially in this setting, given that those aren't words that appear anywhere in my talk slides. That's a low probability thing for me to utter. And you probably had a good sense of that. Like, why is she saying that? That's the reason why language models try to model the probability of text. So how does a language model break that down? Well, a language model actually breaks that down in a really fairly simple way. A language model decomposes, and I promise this is the most probability I'll go into in this talk. A language model decomposes this probability of text into the product of some other probabilities, namely the product of the individual word probabilities given all of the words that have come before them, right? So basically, you know, if you want to write that in formal mathematical notation, it's the probability of token T of the text given tokens 1 through t-1 of the text for the full length of the text. Now, one nice thing about this is that this is actually just the chain rule of probability. Again, if it's been a while since probability for you or you haven't taken it yet, no worries. But the important thing here is that there are actually no simplifying assumptions that are made between converting from this notation and this notation. So actually, we can sort of boil this problem of like, what is the probability of this particular utterance into a bunch of smaller problems about what is the probability of the next word in the sequence, right? So if I've said so far, like the students opened their, you might have like a few different words in mind, right? Like books, laptops, exams, minds, eyes. I don't know. It could be late in the day. And so a language model is going to essentially consider at each step in a sentence or a longer piece of text than a sentence, what's the probability of the next word? Okay, so something else that I should mention is even though I've phrased this as a model whose purpose is to give you the probability of a particular text, you can really easily use this language model to generate text. How do you do that? Well, you start it off with a piece of text, in this case, maybe the, or you can even start it off with just an empty string, just like I'm giving you no context, go. And a language model will essentially sample at each step what is, so what's my probability distribution over the words that come next? And I'm just going to sample from that. And then, so suppose I sample students, I'll just append students onto my context so far and rerun the model. So now I'll have a new probability distribution over what comes next. I'll sample from that, and maybe I'll sample open. And you can actually keep doing this until the model samples the token that tells it to stop. So even though we train the model to predict the probability of which word comes next, it's really easy once you've done that to just flip the model into something that generates new text. So if you hear about language models, that's what this refers to. They're models that predict the probability of the next words. Questions about this? Okay. How long does it take to train or to run this? Oh, okay. Great question, and one that a lot of industry companies are very interested in. Okay. To train, so part of this is parallelizable. So if you're like a company that has a ton of hardware, you can sort of like take less time on training because you're running different pieces of it at different times. But I know for a really good language model, and you're a company with a lot of resources, I would say at least like a month, something like that. If you are not a large company with a massive amount of hardware, this is probably out of your reach to train. That's something that we actually run up against like as researchers all the time. To run a model like this, unless you have, so a lot of the sort of engineers in these companies basically devise ways to try and like cache some information or in some way like take shortcuts or speed up the processing of these models. So that's why if you query ChatGPT, for example, it's relatively fast. If you don't have those sorts of like performance enhancements that engineers have specifically designed for your particular model, then you're looking at maybe like you're lucky like a second per word, but it depends a lot on the size of the model. I can also add up really quickly as we're running a lot of tests. Yeah.
So the generation side, is it generating the same way where it's generating the most probable word given the?
Oh, good question. So there are actually different strategies that people will use for sampling from these probability distributions. The actual sort of vanilla way of sampling won't necessarily generate the most probable word. But if you think about it, like if I have it's kind of like the classic marbles in a jar problem, right? Like if I have, mostly red marbles in this jar, that doesn't mean that if I reach into the jar, I'm necessarily going to draw out a red marble. it means I have a high chance of doing so, but it's not that deterministic, right? That said, one technique that people sometimes use, and by people, I mean the engineers behind these models sometimes use when sampling from them, is to say like, okay, well, we're just going to take the top, say 40 colors of marbles in this jar and throw everything else out. This is something that people research in terms of like how different sampling techniques affect the outputs of these models, but however you can think of sampling from a probability distribution, people have probably tried it. Other questions at this point? Yeah.
Okay, so this is a really simplistic question.
Great.
I think, but this has got to be the idea behind predictive text on your phone.
Yes.
So, but every choice you make, it's like it throws out 3 choices, you make one,
Mhm.
and the next choices are based on the one that you made.
Yes.
So they're not based on something you didn't choose, based on what you did.
Yes.
So it's got to be the same idea.
Yeah.
Those laptops, what follows is going to have something to do with laptops.
Yeah, exactly. And so autocomplete on your phone is actually exactly the right way of thinking about this. If we think about it, that's actually a simpler language model that is hosted on your phone. One of the key differences is it is not a large language model. It's a smaller model, it's more compact, and therefore it hasn't picked up as many patterns from the data. So if you look at, what your phone typically suggests, it's probably not as accurate to what you're thinking as a model like ChatGPT.
But it still learns. Because
Yeah.
you'll notice after a while, if you see, capitalize an R, it knows it's a name, and if you are using a specific name very often, that's going to be one of your choices.
Yes, so I know, and I think, so different tech companies handle this differently. But like Apple, for example, I don't know the exact details of what Apple does. They tend to be fairly, like, once you get into the details of what a particular company does, they tend to be fairly proprietary about it. But yeah, I think Apple, my guess is that they take a pre-trained smallish language model and then occasionally update it based on text that you fed into your phone. Apple tends to be fairly privacy oriented, so I wouldn't be surprised if they did that locally on your phone instead of sending that somewhere else, but I don't know for sure. But yeah, autocomplete is exactly the right way of thinking about this. It's a beefed up autocomplete system. Other questions about language models in general? Still need to get to sort of the main course of ChatGPT. Okay, so to sum up, if we're thinking about neural language models in general, here is the process by which we make them. First, we collect a bunch of training data. This can either be digitized text or it can be born digital text. In fact, if you're looking for digitized text, tends to be much more expensive to get. Unless you're working in like a really specialized like optical character recognition setting for like old texts in libraries or so on, you're probably working with straight web text. What do you do after that? You decide your model's vocabulary. Once you've made this choice, that nails it down. After that, you train a model to predict which words appear around a particular word, like we've seen. So basically just leveraging context clues, this time for neural networks instead of for people learning a vocabulary. Once that model's trained, you basically just remove the last predictive part, take out its word embeddings that it's learned, and plug them into a model that will actually learn to perform language modeling. In other words, you will keep training the whole neural network to predict the probability of the next word. So not just this sort of cloud of words that appears around a word, but the next word in the sequence. Okay, I think that's mostly just a summary of what we've talked about so far. Okay, so let's shift gears to thinking about more recent models. So now if some of you have taken NLP, you might be thinking, wait, but okay, so we talked about language models. Everything that I've described so far, we've been doing in natural language processing for a decade. You haven't been hearing about models like ChatGPT for a decade. What changed? There are a few things that changed. So I would say these 3 main factors that changed are as follows. First, ChatGPT and other other recent models developed by OpenAI in particular, take this same sort of idea that we talked about like shifting the landscape slightly of your loss function, and they take it one extra step. Once we've trained a language model, we will use those parameters as a starting point to train a model to follow written instructions. So basically they do some, if some of you are really enthusiastic about the machine learning behind this, they do some reinforcement learning to basically re-rank outputs based on whether they seem to fit with people's preferences. So that's one thing, but I would say these last two things are the more important things. One of the big changes has been sort of seismic shift within NLP, so natural language processing, about how we capture the context of a word. The idea that I gave you about how we capture the context of a word, it's still sort of the underlying backbone of a lot of what we think about in NLP these days, but we've refined that idea. We now have even better ways of taking into account the context of not just that word in the training data, but also the context of the particular sentence that you're giving it, or the particular prompt that you're giving it. The third thing is way more training data, far more training data than we were using 10 years ago. And there are reasons that there are factors that have enabled us to use more training data, essentially, which I'll get into. So to give a little bit more, I think this one probably not worth going into too much detail on this, in part because the details of this are sort of kept, like OpenAI has those details and has not released a lot of them. So I'll talk more about what goes into these two factors. First, okay, so we've talked about how to learn the meaning of a word from context clues. But let's think about a word like bank, right? Well, if I say the word bank and I don't say anything else around bank, well, that could mean one of at least three things, I think. Actually, no, it can definitely mean more than that. It can mean a financial institution. It can mean turning a plane, so to bank a plane, or it can mean a river bank. As I'm thinking about it, it can also mean the verb of interacting with a financial institution, right? So there's a decent amount of content that's captured in this one little word. And if we're just like automatically learning meaning from text, we're not going to be able to distinguish between these that well. We're going to learn a single set of parameters or bank that is supposed to cover all three of these totally separate meanings. And frankly, most of those meanings are, well, in fact, two are not going to be relevant when this word comes up, right? It's going to be one meaning. So how do we deal with this problem? Okay, well, recent advances in NLP have enabled us to make way more use of not just the training data, but also the prompts that we give a language model. So essentially, if we see at training time, right, or sorry, not at training time, after we've trained the model, the parameters of the model are all fixed, and at this point, we're just trying to get what's the model's output for a particular input. If I see we banked to the right, in the past, we would have had to, well, like, okay, are we banking? Isn't like a financial institution? Okay, we'll bank to the right, whatever that means. Current models are far better at saying to the right. Okay, sift out the part of the meaning that has to do with financial institutions we're probably turning. Likewise, the town bank was a venerable institution, right? These, like the words that appear around the appearance of a particular word are informative, you know, just like they are for us as people about which meaning is being used. And this applies even to like more, like, interestingly, this applies even to more difficult sentences, right? So like even though Wall Street Journal might typically be associated with bank in the financial sense, current NLP models are actually, in a lot of cases, capable of distinguishing, even in this case, no, this is probably a riverbank in this case. That better use of context based on the actual prompts that you gave the model has been huge for improving the performance of language models. Huge. Okay, in particular, I don't have, if I had like, if I had like 5 more lectures, which I don't, then I might be able to talk about the transformer model architecture and talk about what makes it tick. I don't have 5 more lectures. I got this one. So what I'm going to say is that if you hear the term transformer thrown around, it refers to a way of configuring the parameters of a neural network that essentially encodes this kind of context passing. That's just an integral part of the network. And so someone coming up with that network was essentially what allowed for this better use of context based on the prompt you gave it. Okay, so let's talk about more training data. You know how I mentioned that the transformer is kind of important for context. It turns out the transformer is also the key thing behind allowing us to process more training data. So the transformer, let me think about how to say this. Have you ever sorted through like a giant stack of papers looking for not just one thing, but like a sequence of things? Like we're trying to sort those somehow, and maybe you haven't taken computer science, so sorting algorithms are maybe not something that's on your mind at that point. There tends to be like a trade-off between the space that you make that stack of papers take up and the time that it takes you to sift through that stack of papers for what you're looking for, especially for the sequence, right? You keep everything in a single stack, right? And you keep sifting through every time looking for something. Okay, well, we've kept space low. We're going to take more time. If on the other hand, you're like me, you end up with your bedroom completely covered with a bunch of little stacks of paper where I'm like, okay, this is a mess, but I'm faster at knowing, like, okay, here's my stack of papers corresponding to this. The same basic idea applies for computer science as well. Space and time are a huge trade-off within computer science. The transformer takes a ton of space on a machine, but it does so in a way that allows for less time in order to calculate the nudges that each instance of training data need to give to parameters. Is the shortest way I can explain that, I think. Whoa, that's interesting. Let's go back to this. Interesting. Okay. Wait for it. Once again. Yay. Okay, great. Interesting. Yeah, so basically, what does this mean? Okay, well, if it takes less time to train a model, well, this means that companies, namely the ones of us who have a lot of computing resources, before they were waiting just as long as we were for the same sorts of models to train. But if a model just trains faster now, well, there's no reason why you can't just train the model for the same amount of time you would have trained it before and just train on a lot more data. So basically, they're using the extensive hardware that they have to allow them to get through a lot more training data faster. In other words, current large language models have seen so much more training data than any language model we had as of like a couple of years ago. Okay, so this brings me to talking about data. Which data is actually used to train large language models? Well, web text. Beyond that, it's actually really tough to give a more specific description than that. This fully has to do with just the magnitude of the text that's scraped. This is easily more text than a human would see in their lifetime. It's a large chunk of the internet. That said, that's not to say there hasn't been like some research trying to characterize this data. I'm going to link to a couple of papers that like lab mates of mine have done. But the fact that figuring out what is in these data sets is a research direction in itself tells you how much we're unsure of exactly what text is in there. There's also questions about like, okay, well, for a lot of these companies that are developing these language models, they'll filter out some text in advance. But there are big questions that come up then about like, okay, well, what kinds of text is getting filtered out? Is it just like automatically generated text, or is it maybe other dialects of English, for example, that don't necessarily follow this, like all of the same grammatical rules as the one that I'm speaking right now? Is it, like code switching language that goes back and forth between two or more different languages? Possibly, we're not sure. But figuring out what data these models are trained on is an ongoing research direction. Yeah.
If they're being trained on the data, how do we not know what it is? Is it because it's industry secrets, or is it because we just don't want to look through 50 billion text on it?
Honestly, it's part of both. So I don't believe that for like the current large language models that you're hearing about, I don't think OpenAI has released the exact list of everything that they use, never mind hosting it somewhere. To be honest, I'm not sure. I am not totally positive that they even know. Because this is like a large enough amount of data, right? Where like, are you updating it constantly? Do you know which version of your model has been trained on which data? If you're not super careful about documenting that, some of those details can get lost. And if you've ever worked with a large data set before, you have a good sense of how easy it is for some of these small details to fall through the cracks. So I wouldn't be surprised if like, so I don't know exactly what's in there. I wouldn't be surprised if like that's also the case for OpenAI employees. Yeah.
I'm not sure this is a question, I'm just trying to get through this, but basically, if you're not paying attention to what kind of data you're looking at, what kind of data you're using to train this model, then there could be vast, really extensive things that are being left out and no one knows.
Yes.
Which means that you're affecting the outcome and no one knows it, or why.
Yes.
No one knows why, maybe it's a better way.
That is exactly right.
So, yeah, you could be developing a really biased model.
Yeah, I'm gonna talk about that. So there's a reason why, so sort of talking about like, okay, why are these research directions? Why do we care about what's in the data? It's for exactly that reason. The training data has a direct impact on the kinds of outputs that the model will produce after it's been trained. And if we don't have a good sense of what informs the model's training, then we don't have a good sense of what to expect from it in terms of the outputs it produces. Okay, so that said, what does this mean that ChatGPT is good at? What do all of these details about how it's trained, what it's trained to do mean that it's good at? Well, in short, predicting which word comes next. I don't know how many of you have played Mad Libs. I feel like I was really into these in like first grade. Also, if you play them with like a kid and there's a noun, poop is guaranteed to be called out. But you can kind of think of what these models do as basically playing an extremely vanilla version of Mad Libs. Instead of trying to generate surprising words, right? That like, like this makes no sense in context. The model essentially reads through the words and does its very best to figure out, given everything that's come before it, what is the most likely thing to happen next, based on the data I've seen. So that basically summarizes it. What are some aspects of producing answers that fall under this category? Okay, well, writing in specific styles, first of all, right? Like if I'm speaking like classic, like pseudo Shakespeare, right? Then the probability of thou appearing, relatively soon is a lot higher than it is in my normal speech. So the key thing here is that we have to know these have to have appeared in the model's training data in order for the model to have actually, absorbed anything about the style. Also, grammatical consistency. These models tend to be pretty good at that. It's highly related to figuring out, like, okay, what kind of word comes next, like the sense of a verb or something. Tenses. They tend to be pretty good at that. Also, if you've ever asked ChatGPT to generate something, you might notice that generating boilerplate sentences that often appear towards the beginnings or ends of emails, for example, oh, ChatGPT has got those on lock. It's seen those so many times. All of these can basically be summed up as fluency. My advisor, Noah Smith, calls these sorts of models fluency machines. And I don't think that's far off. It turns out you can pick up a lot of things that we would consider to be content through fluency, but these models are essentially just optimized to be as fluent as possible over the training data. Okay, that's it in the last few minutes. So that's what ChatGPT is good at. What are some problems that ChatGPT's training leaves it prone to? Well, first of all, inaccuracies, right? If you're just predicting, like we already talked about how to generate from these models, right? You just like over and over again, generate a new probability distribution over the word that comes next and sample from it. That means the language model isn't doing any higher level planning about what it says in advance, not explicitly anyway. And so if you're looking for like a particular fact appearing in an answer, maybe the model has seen text about that enough times for it to just kind of generate that. But that's not guaranteed. It's not like a planned answer that it's retrieved. Also, the appearance of one word might make other words that have appeared around that word in the past more likely, even if the context is mixed up. I particularly like thinking about, so there was a natural language processing paper that was published at a conference a couple of years ago. It was called Barack's wife Hillary, which again, like we know that that's not true, but if you think about the text that these models are trained on, like they titled this precisely because at the time, this was a super easy sort of mistake for these models to make. Barack and Hillary tended to appear in a lot of the same text. And so if you're just generating more text, well, then there's a good chance you'll just sample something that tends to appear in the same sorts of contexts. And also, the model doesn't actually store facts. It has a bunch of parameters that is basically adjusted to try and capture as many patterns as it can about the training data to inform it about what word's likely to come next. But there's no explicit storing of facts anywhere in there. And so these sorts of things leave the model prone to inaccuracies, especially if you're looking up something that is like a slight twist on a lot of text that's appeared before. Or something that hasn't appeared in much text at all. These kinds of things can trip the model up. Also, related, lack of source attribution. So just like the model doesn't sort facts, it also doesn't sort sources. So I asked a fellow PhD student in the computer science department at UW Seattle messaged us, a few weeks ago, like, I wish I could speak with the confidence of ChatGPT when asking about its sources. So he works on computer science theory, right? So again, if you're into theory, then some of these words might ring a bell. I should mention all of these papers are fake. ChatGPT just kind of like they don't exist. ChatGPT, when asked for its sources, did what basically like someone bluffing their way through a job interview would do, and just kind of lists words that sound good, but they're not actually like a stored thing. So that's an issue. And finally,
And these links will go to random YouTube links.
or like 404 problems or something.
I have tried to do this for research papers. I give 5 sources about a topic I need to write about. And then I looked it up, like, oh, these don't exist.
Yeah.
Thanks.
Yeah. So 404 errors are probably really common. Maybe you get lucky and you hit on a completely different paper, like you got the link, but for something else. And then finally, outputs that reflect social biases, as kind of alluded to before, right? So this is an example. It's not a super current example, but I think it does a really good job of illustrating the problem. So this is from a machine translation system a few years back, right? So there's been more work on this since then. But this was a machine translation system that was trained to go between Hungarian and English. Now in Hungarian, right, the pronoun that's used is like genderless, right? Like doesn't specify which gender we're talking about. Now in the training data, based on the training data, nurse appearing around female pronouns is more likely. Scientist appearing around male pronouns is more likely. All of these were even just a little bit more likely. But for a model that is essentially trying to predict the highest probability thing that comes next, a little bit more likely is good enough for that model. That's more likely to be generated. And so this isn't like limited to machine translation either. Like anything that you can think about where like text on the internet has certain words more likely to appear near other words, ChatGPT will pick that up. On that note, I think I am out of time, but I'll take questions if people have them. Thanks, everyone.
So thank you everyone for attending. This was the last talk of this month, but we will have 2 remaining talks as we're getting closer and closer to summer on cloud computing for next month. So look forward to those emails in UWT line. Sophia will be around for a couple more minutes if you have any questions, but thank you again, everybody, for showing up, and let's give Sophia another round of applause for being such an amazing speaker. Thank you all, and thank you to all on Zoom, and we'll see you all later.